Quasars. Quasars, short for quasi-stellar radio sources, were first discovered in the early 1960s, when astronomers detected strange points of light that appeared star-like but emitted radio waves, and exhibited extreme redshifts, indicating they were incredibly far away. The first confirmed quasar, 3C273, was identified by Martin Schmidt in 1963. It became clear that these were not stars at all, but the extremely bright and energetic cores of distant galaxies powered by supermassive black holes. At the center of each quasar lies a black hole millions to billions of times the mass of the Sunday. As gas, dust, and even stars spiral into the black hole, they form an accretion disk that heats up through friction to millions of degrees, emitting radiation across the electromagnetic spectrum. Quasars are capable of outshining entire galaxies. Some release 1,000 times more energy than all the stars in the Milky Way combined. The terrifying aspect of quasars is their raw, destructive power. The radiation they produce, especially in X-ray and ultraviolet, can travel across billions of light years. Their relativistic jets, launched from the poles of the spinning black hole, can stretch for millions of light years, acting like cosmic blowtorches that strip gas from galaxies and sterilize any planetary systems caught in their path. Fortunately, most quasars are located in the early universe. Because they formed billions of years ago, their light is only now reaching Earth. Today, fewer quasars are active because their central black holes have consumed most of the available matter. But the fear remains. If a quasar were to form near our galaxy, its radiation would wipe out Earth's atmosphere, render the planet uninhabitable, and disrupt or destroy any trace of life. We are lucky that the few quasars visible from Earth are billions of light years away, because up close, they are among the most hostile environments the universe can produce. Magnetars. Magnetars are a rare and extremely dangerous type of neutron star, first theorized in the early 1990s and confirmed through the observation of unusual gamma-ray bursts known as soft gamma repeaters. These compact stellar remnants are formed when a massive star undergoes a supernova explosion, leaving behind a dense core that collapses into a neutron star. In the case of magnetars, this remnant develops an ultra-powerful magnetic field, making it one of the most extreme objects in the cosmos. A typical neutron star already compresses more mass than the Sun into a sphere only about 20 kilometers across, but a magnetar's magnetic field is what sets it apart. It can be up to a quadrillion times stronger than Earth's magnetic field. This kind of magnetic intensity is not just theoretical, it's so strong that if a magnetar were located as far as the Moon, it could wipe every credit card on Earth, disrupt all electronic devices, and even distort atomic structure. What makes magnetars terrifying isn't just their power, it's their instability. Their magnetic fields twist and fracture the star's crust, occasionally releasing massive bursts of X-rays and gamma rays in a fraction of a second. One such flare in 2004, from a magnetar called SGR 1806-20, released more energy in 0.2 seconds than the Sun emits in 250,000 years. If it had been only a few light years closer, it could have devastated Earth's atmosphere. Magnetars are unpredictable, violent, and very poorly understood. They don't announce themselves with visible light or heat, but with sudden, invisible radiation blasts that could fry spacecraft and cripple global infrastructure if one ever formed too close. There are currently about 30 known magnetars, most of them thousands of light years away. But given how difficult they are to detect, astronomers believe there could be many more lurking throughout the galaxy. If even one were to activate within dangerous range, it could become a cosmic weapon, an invisible bomb in the sky detonating without warning. The dark flow. The dark flow is one of the most mysterious and unsettling large-scale phenomena in cosmology. It was first detected in 2008 by astronomers using data from NASA's Wilkinson Microwave Anisotropy probe. The researchers observed that clusters of galaxies were all drifting in the same direction, toward a specific region of the sky, at velocities exceeding 600 kilometers per second without any identifiable cause. What makes the dark flow so alarming is that this motion cannot be explained by any known gravitational structure within the observable universe. Galaxy clusters as far as 2.5 billion light-years away are all being pulled in the same direction. Yet nothing in that region, no superclusters, voids, or anomalies appears massive enough to account for the effect. Some scientists believe this might point to the existence of a massive structure beyond the edge of the observable universe, something so enormous and influential that it tugs on galaxy clusters across billions of light-years. Others have speculated more radically that it could be evidence of a multiverse, a realm beyond our known universe, exerting a gravitational pull we cannot see. The unsettling part of the dark flow is its implication that the universe may be larger, stranger, and more dangerous than we ever imagined. If this effect is real and not an observational error, it suggests that unseen forces outside our cosmic horizon are interacting with our universe. We can't see them, measure them directly, or understand them using current models of physics. To this day, the dark flow remains a subject of debate. Some studies using newer data, like the Planck satellite, have failed to reproduce the original results, while others continue to find hints of consistent movement. But the possibility that something unknown, possibly outside of space-time as we know it, is pulling on the largest structures in the cosmos is enough to make it one of the scariest ideas in modern astrophysics. Rogue black holes. Rogue black holes are solitary black holes that drift through space untethered to any galaxy, invisible and silent. While black holes are typically found at the centers of galaxies or within stellar systems, rogue black holes are ejected from their host galaxies through powerful events such as galactic collisions, gravitational interactions, or the violent collapse of massive stars. Their theoretical existence has long been accepted, but it wasn't until 2022 that NASA confirmed the first potential detection of a rogue black hole about 5,000 light-years from Earth using gravitational microlensing. What makes rogue black holes terrifying is their complete stealth. They do not emit light, radiation, or any electromagnetic signals unless interacting with nearby matter. Without accretion disks or surrounding material, they are effectively invisible to conventional observation techniques. The only way to detect one is through the way it bends and magnifies the light of background, stars an effect that requires precise alignment and is extremely rare to observe. Once ejected from a galaxy, a rogue black hole can wander through interstellar or intergalactic space for billions of years. If one were to pass through a star system, it could disrupt planetary orbits, tear apart stars, or even swallow entire planets, all without warning. Earth would have no way of detecting its approach until gravitational effects began to distort space locally, and by then, it would be too late to escape. Estimates suggest that the Milky Way alone could harbor millions of these rogue black holes, silently roaming the galactic outskirts or even passing through the disk unnoticed. Because they are black holes without an anchor, they represent cosmic bullets, traveling blindly through space and capable of total destruction without a trace. What makes them among the scariest phenomena in the universe is their combination of power and unpredictability. A rogue black hole doesn't announce itself. It doesn't shine. It simply moves quietly, invisibly, and obliterates anything in its path. TON 618. TON 618 is one of the most powerful and terrifying objects ever discovered in the known universe. It was first cataloged in the 1950s during a survey of blue stellar objects, but its true nature wasn't understood until the 1970s, when astronomers realized it wasn't a star at all. It was a quasar, powered by a supermassive black hole of unimaginable proportions. Located approximately 10.4 billion light-years away, TON 618 is so distant that we see it as it existed just a few billion years after the Big Bang. At its center lies a black hole with an estimated mass of around 66 billion solar masses, making it one of the largest and most massive black holes ever detected. For comparison, the supermassive black hole at the center of the Milky Way, Sagittarius A, is only about 4 million solar masses. TON 618 is over 16,000 times more massive. What makes TON 618 so unsettling is its scale and energy output. The quasar emits more light than entire galaxies, and the energy released by its accretion disk is enough to be seen across the visible universe. The amount of matter falling into the black hole is so enormous that it outshines all the stars in its host galaxy combined, sending jets of radiation and plasma tearing through space. This raises fundamental questions about how such an object could even form. Conventional models of black hole growth struggle to explain how TON 618's central black hole reached its size in such a relatively short time after the birth of the universe. It suggests that black holes can grow faster and larger than we thought possible, potentially altering how we understand galactic evolution. TON 618 isn't just dangerous in theory. It represents the upper limit of gravitational consumption, a cosmic monster that dwarfs even the most extreme phenomena. If such an object were closer to us, it would be capable of evaporating atmospheres, tearing stars apart, and warping space on intergalactic scales. Its presence reminds us that in the depths of space, there exist entities so massive and powerful that they stretch the limits of physics and our own cosmic insignificance. The edge of the observable universe. The edge of the observable universe isn't a physical boundary, but a cosmic horizon, a limit set by the age of the universe and the speed of light. Light takes time to travel, and since the universe is about 13.8 billion years old, we can only see as far as light has had time to reach us. But due to cosmic expansion, that distance isn't 13.8 billion light-years, it's actually about 46.5 billion light-years in every direction. This defines a sphere around Earth known as the observable universe. The concept was developed in the mid-20th century, following discoveries about cosmic expansion and the Big Bang. As space itself stretches, galaxies farther away recede from us, faster than the speed of light, not because they're moving through space quickly, but because the fabric of space between us is expanding. What makes the edge of the observable universe so terrifying is what lies beyond it, nothing we can ever know. Anything past that boundary is forever invisible, not because it doesn't exist, but because light from those regions will never reach us. These galaxies and structures are not only unreachable, they are unknowable, permanently separated from us by the expansion of space itself. Even more unsettling is that galaxies near the edge are moving away so fast that their light will eventually stretch beyond detection. As time goes on, these galaxies will disappear from view forever, leaving the universe darker, emptier, and more isolated. This means that the observable universe is shrinking in terms of what we'll be able to see in the distant future. The edge of the observable universe represents more than a distance, it is a barrier to knowledge. Beyond it could lie an infinite expanse of galaxies, unknown forms of matter, different physical laws, or even other universes. We will never know. Not because we lack the technology, but because light and therefore information cannot cross that boundary. It is the ultimate isolation, a cosmic wall that defines the limits of what we can observe, measure, or even imagine. And as the universe continues to expand, that wall will keep moving farther out, pulling the rest of existence away from us into eternal silence. False vacuum decay. False vacuum decay is not a place, but a cosmic threat embedded in the very structure of reality. It arises from quantum field theory, particularly our understanding of the Higgs field, which is responsible for giving particles their mass. According to some interpretations, the universe may not be in its most stable possible energy state, what physicists call the true vacuum. Instead, we may be trapped in a false vacuum, a temporary, metastable state that appears stable but isn't. This idea first gained traction following the discovery of the Higgs boson in 2012. When physicists plugged the Higgs boson's mass, around 125 GeV, and the top quark's mass into equations, the results suggested that the vacuum of our universe might be metastable, meaning it could spontaneously collapse under the right conditions. If that were to happen, a small bubble of true vacuum would form somewhere in the universe and begin expanding outward at the speed of light. This bubble would rewrite the laws of physics inside it, changing constants, particles, and the very fabric of space-time. Any matter it touched, including galaxies, stars, and planets, would be instantly annihilated. Earth would vanish before any warning could be detected. What makes false vacuum decay so terrifying is its total unpredictability and unstoppable nature. It would occur without any signal. There would be no flash, no gravitational wave, no forewarning of any kind. It wouldn't just destroy life, it would overwrite reality. Electromagnetism might cease to function, atoms might no longer bind, and the universe itself could become a cold, lifeless void governed by alien physics. The only reason we continue to exist may be because the process hasn't randomly started yet, or because quantum tunneling events like this are incredibly rare on human timescales. But mathematically, the possibility exists, and it is encoded into the very equations that describe our universe. False vacuum decay is not just the death of a planet or a star. It's the death of everything, everywhere. Instantly, a universal reset, wiping out the cosmos as we know it. Vacuum metastability. Vacuum metastability represents one of the most fundamental threats to existence itself. The Higgs field, which gives all particles their mass, currently sits in what physicists call a false vacuum state. This means the field exists in a temporary energy configuration that appears stable but is not the lowest possible energy state. Think of a ball sitting in a shallow depression on a hillside. It looks stable, but if disturbed, it could roll down to a much deeper valley below. The true vacuum state would have completely different physical properties. If the Higgs field were to spontaneously tunnel to this lower energy state, it would create a bubble of altered physics expanding outward at the speed of light. Inside this bubble, the fundamental constants of nature would change. Atoms would no longer bind together the same way. The strong nuclear force might weaken. Electromagnetic interactions could cease to function as we know them. This transition would happen without warning. There would be no advanced signal, no gravitational waves, no electromagnetic radiation to alert us. The bubble wall would simply arrive, rewriting the laws of physics as it passed. Everything in its path, galaxies, stars, planets, and all matter, would be instantly restructured according to the new physical laws or simply cease to exist. Current calculations suggest our vacuum state is metastable, meaning it could theoretically decay, but the probability is extraordinarily low on human timescales. However, high-energy events like cosmic ray collisions or the formation of microscopic black holes could potentially trigger this transition. The uncertainty lies in our incomplete understanding of quantum field theory at the highest energy scales. Primordial black holes. Primordial black holes formed in the first fraction of a second after the Big Bang, when extremely dense regions of space collapsed under their own gravity. Unlike stellar black holes that form from dying stars, these ancient objects could have masses ranging from less than a gram to millions of solar masses. They represent some of the earliest and most mysterious structures in the universe. These black holes formed when quantum fluctuations in the early universe created regions dense enough to overcome the outward pressure of radiation. The process required density variations of at least 30% above the average cosmic density. Most of these fluctuations were smoothed out by cosmic expansion, but the largest ones collapsed into black holes within the first microsecond of cosmic history. What makes primordial black holes particularly terrifying is their potential abundance and invisibility. Theoretical models suggest they could make up a significant portion of dark matter, the mysterious substance that comprises 85% of all matter in the universe. This means millions or billions of these invisible gravitational traps could be scattered throughout our galaxy, drifting silently through space. Small primordial black holes, those with masses less than a mountain, would have evaporated completely through Hawking radiation by now. But larger ones persist indefinitely. A primordial black hole with the mass of Earth would have an event horizon only 9 millimeters across, making it virtually impossible to detect unless it actively consumes matter. The most disturbing possibility is that one of these objects could be wandering through our solar system right now. Unlike stellar black holes, which announce their presence through X-ray emissions from heated matter, a solitary primordial black hole would remain completely dark until something crossed its path. Strange stars. Strange stars represent a theoretical form of matter, so exotic that they challenge our understanding of nuclear physics. These objects would form when the intense pressure inside a neutron star becomes so extreme that it converts ordinary matter into strange quark matter, creating a fundamentally different type of stellar remnant. Normal matter consists of protons and neutrons, which are themselves made of up quarks and down quarks. Under the crushing conditions inside a neutron star, these particles can be compressed beyond their normal limits. If the pressure exceeds a critical threshold, the up and down quarks transform into strange quarks, creating a soup of free quarks rather than bound particles. Strange quark matter has properties that defy conventional physics. It would be absolutely stable at any pressure, meaning it represents the true ground state of matter rather than the atoms we observe in everyday life. This stability comes from the strange quark's ability to occupy lower energy states than conventional nuclear matter, making strange matter more tightly bound than even atomic nuclei. The terrifying aspect of strange stars lies in their potential for conversion. If strange quark matter is truly more stable than normal matter, then any contact between strange matter and ordinary matter would trigger a chain reaction. The normal matter would convert to strange matter, releasing energy and spreading the conversion process outward like a cosmic infection. A strange star would appear similar to a neutron star from a distance, but its surface would be fundamentally different. Instead of a solid crust of atomic nuclei, it would have a smooth surface of pure quark matter. The boundary between the star and empty space would be sharp and well-defined, unlike the fuzzy atmosphere of normal stars. If strange stars exist, they could be scattered throughout the galaxy, indistinguishable from neutron stars until detailed observations reveal their true nature. The possibility that ordinary matter is not the most stable form of matter in the universe suggests that everything we see around us exists in a metastable state, vulnerable to conversion by contact with strange matter. Kugelblitz, black holes. Kugelblitz black holes form not from collapsing matter, but from pure concentrated energy. The name comes from German, meaning ball lightning, and describes a theoretical black hole created when electromagnetic radiation becomes so intensely focused that it curves spacetime enough to trap light itself. This represents one of the most exotic ways a black hole can theoretically form. Einstein's mass-energy equivalence principle states that energy and mass are interchangeable. When enough energy concentrates in a small enough region of space, it can create the same gravitational effects as an equivalent amount of mass. For a Kugelblitz to form, the energy density must reach approximately 10 to the 67th joules per cubic meter, a concentration so extreme that it exists only in theoretical calculations. The formation process would require focusing enormous amounts of electromagnetic radiation, such as gamma rays or high-energy photons, into a region smaller than the resulting black hole's Schwarzschild radius. At this point, the energy itself becomes gravitationally bound, creating an event horizon from which even the light that formed it cannot escape. What makes Kugelblitz black holes particularly unsettling is their potential for artificial creation. Unlike stellar black holes that require the collapse of massive stars, a Kugelblitz could theoretically be manufactured using advanced technology capable of concentrating sufficient energy. This raises the possibility that sufficiently advanced civilizations could weaponize black hole formation, creating gravitational weapons of unimaginable destructive power. Natural Kugelblitz formation remains highly speculative, but certain extreme astrophysical events might generate the necessary energy concentrations. The collision of multiple gamma-ray bursts, the focusing of cosmic rays by gravitational lensing, or the interaction of matter and antimatter in specific configurations could potentially create the conditions for spontaneous Kugelblitz formation. These energy-based black holes would behave identically to mass-based black holes once formed, but their origin from pure radiation represents a fundamental demonstration that energy and matter are truly equivalent at the most extreme scales of physics. White holes. White holes represent the theoretical opposite of black holes, regions of spacetime that expel matter and energy rather than consuming it. While black holes have event horizons that prevent anything from escaping, white holes would have event horizons that prevent anything from entering. These objects exist as mathematical solutions to Einstein's field equations, but have never been observed in nature. The concept emerges from the time-reversed mathematics of black hole physics. If you run the equations for a black hole backward in time, you get a white hole that spews out matter and energy continuously. The event horizon of a white hole acts as a one-way barrier in the opposite direction, allowing matter and radiation to exit but forbidding any external material from crossing inward. White holes would violate the second law of thermodynamics by continuously decreasing entropy in their local region. They would spontaneously create order from chaos, ejecting organized matter and energy into the universe without any apparent source. This creates a feedback loop where the white hole's own emissions prevent anything from falling into it, but also make the surrounding region increasingly chaotic and energetic. Some cosmologists have speculated that the Big Bang itself might have been a white hole event, the ultimate expulsion of matter and energy into an empty universe. This would make our entire observable universe the product of a single, massive white hole that existed for an infinitesimally brief moment before exhausting itself. If white holes exist, they would appear as brilliant sources of matter and energy with no apparent fuel source. They would shine continuously, ejecting particles and radiation at tremendous rates, while remaining completely inaccessible to external influence. The energy output would be enormous and unpredictable, making any nearby region of space extremely hazardous. Naked singularities. Naked singularities represent one of the most terrifying violations of cosmic censorship in theoretical physics. Unlike the singularities hidden within black holes, a naked singularity would be a point of infinite density and curvature exposed directly to the universe, unshielded by an event horizon. This exposure would allow the singularity to interact directly with the outside world in ways that could fundamentally break causality. The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that nature prevents naked singularities from forming by always surrounding them with event horizons. This protection is crucial because singularities represent points where the known laws of physics break down completely. Space and time become infinitely curved, density becomes infinite, and mathematical descriptions of reality cease to function. A naked singularity would form if a massive object collapsed without generating an event horizon, or if an existing black hole lost enough mass through Hawking radiation that its event horizon disappeared before the singularity evaporated. They could violate conservation laws, create closed timelike curves that allow time travel, and generate effects that propagate faster than light. Near a naked singularity, the curvature of spacetime would become so extreme that tidal forces would stretch and compress matter in impossible ways. The gravitational field would be so strong that it could tear apart atomic nuclei, but unlike inside a black hole, this destruction would be visible to outside observers and could influence the rest of the universe. The most disturbing possibility is that naked singularities could act as sources of completely unpredictable phenomena. They might spontaneously create matter, emit bursts of exotic particles, or generate gravitational waves with no apparent cause. The breakdown of physical laws at the singularity means that literally anything could emerge from these points, making them cosmic wildcards that could reshape reality without warning. Phantom dark energy. Phantom dark energy represents a theoretical form of dark energy, with an equation of state parameter less than -1, meaning its density increases as the universe expands rather than decreasing. This violates the null energy condition, a fundamental assumption in general relativity that prevents energy density from becoming arbitrarily negative. If phantom dark energy exists, it would drive an accelerating expansion so extreme that it would eventually tear apart every structure in the universe. Normal dark energy, which comprises approximately 70% of the universe, has a constant density as space expands. This creates a repulsive gravitational effect that accelerates cosmic expansion at a steady rate. Phantom dark energy would behave differently, becoming denser and more powerful as the universe grows larger, creating a runaway acceleration that grows stronger over time. The equation of state parameter, denoted as W, determines how dark energy behaves during expansion. Normal matter has W equals 0. Radiation has W equals 1/3. And cosmological constant dark energy has W equals -1. Phantom dark energy would have W less than -1, meaning its pressure becomes more negative than its energy density, violating fundamental energy conditions. This violation leads to catastrophic consequences for the future of the universe. As phantom dark energy becomes denser, its repulsive effects grow stronger, accelerating expansion at an ever-increasing rate. Eventually, this acceleration would overcome all other forces in nature, including the strong nuclear force that holds atomic nuclei together. The timeline for phantom dark energy destruction would follow a predictable sequence. First, galaxy clusters would be torn apart as space expands faster than gravity can hold them together. Then, individual galaxies would dissolve as stars are pulled away from each other. Solar systems would disintegrate as planets are ripped from their orbits. Finally, in the last moments, atoms themselves would be torn apart as the expansion of space overcomes electromagnetic and nuclear forces. Current observations of cosmic acceleration are consistent with a cosmological constant, but the uncertainty in measurements leaves room for phantom dark energy as a possibility. If future observations detect W becoming more negative than -1, it would confirm that the universe is heading toward this ultimate destruction, with no possible escape or prevention. Closed timelike curves. Closed timelike curves represent regions of spacetime where the geometry becomes so warped that time loops back on itself, creating paths through spacetime that return to their own past. These mathematical solutions to Einstein's field equations allow for the theoretical possibility of time travel, but they also create paradoxes that could fundamentally break causality and the logical structure of reality. The curves form when extreme gravitational fields or exotic matter configurations bend spacetime so severely that the normal flow of time becomes twisted. In these regions, an object following its natural path through spacetime could theoretically travel into its own past without exceeding the speed of light or violating local physical laws. The curvature of spacetime itself provides the mechanism for backward time travel. Several theoretical scenarios could generate closed time-like curves. Rotating black holes, known as Kerr black holes, contain regions called ergospheres, where spacetime is dragged around so violently that closed time-like curves become possible. Cosmic strings. Hypothetical one-dimensional defects in spacetime could create closed time-like curves if two strings passed by each other at high speed. Alcubierre warp drives, theoretical faster-than-light propulsion systems, could also generate these temporal loops as a side effect. The existence of closed time-like curves would create grandfather paradoxes and other logical contradictions. An observer could theoretically travel back in time and prevent their own birth, or deliver information to their past self that they only learned by receiving it from their future self. These paradoxes suggest that either closed time-like curves cannot exist in nature, or that some unknown mechanism prevents paradoxes from occurring. The Novikov self-consistency principle attempts to resolve these paradoxes by suggesting that the laws of physics would somehow conspire to prevent any action that would create a logical contradiction. Events would arrange themselves so that any attempt to change the past would fail, or would turn out to have been part of the original timeline all along. In cosmological models with infinite time or space, Boltzmann brains become not just possible but inevitable. If the universe continues expanding and cooling forever, reaching a state of maximum entropy, random quantum fluctuations will eventually produce every possible arrangement of matter. This includes countless Boltzmann brains, each existing for brief moments with complete false memories of lives they never lived. The terrifying implication is that if Boltzmann brains vastly outnumber naturally evolved conscious beings, then statistically, you are more likely to be a Boltzmann brain than a real person. Your memories of childhood, education, and experiences would be illusions created by random particle arrangements. The entire universe you perceive could be a false construction of a fluctuating brain destined to dissolve back into chaos within moments. This paradox suggests that either our cosmological models are wrong, or that consciousness and observation work in ways we do not understand. Some physicists argue that the Boltzmann brain problem indicates flaws in our theories about the ultimate fate of the universe, while others propose that conscious observation itself plays a fundamental role in determining which configurations of matter can exist. The existence of Boltzmann brains would mean that most conscious experiences in the universe are brief, isolated, and based on completely false information about reality. It represents the ultimate cosmic horror. The possibility that consciousness itself is mostly an illusion experienced by randomly assembled matter in an otherwise empty and meaningless universe. The heat-death plateau. The heat-death plateau represents the final equilibrium state of the universe, a period lasting incomprehensibly longer than all previous cosmic history combined. After the last stars burn out and black holes evaporate through Hawking radiation, the universe will enter a state of maximum entropy where no further work can be performed and no complex structures can exist. This plateau begins approximately 10 to the 100 power years from now, when the last stellar remnants fade and the cosmic microwave background radiation cools to near absolute zero. At this point, the universe will consist primarily of elementary particles, photons, and neutrinos distributed uniformly throughout an ever-expanding space. The temperature will approach absolute zero, but never quite reach it due to the continued expansion of space. During the heat-death plateau, the universe will be dominated by quantum vacuum fluctuations. These random variations in energy will occasionally create temporary structures, including particles, atoms, and even complex molecules. But these formations will be extremely rare and short-lived. The average time between significant fluctuations will be measured in periods so vast that they dwarf the current age of the universe by factors of trillions upon trillions. The most disturbing aspect of the heat death plateau is its duration. While the universe has existed for approximately 14 billion years, the heat death plateau will last for an essentially infinite amount of time. All of cosmic history up to this point represents an infinitesimally brief moment compared to the eternal emptiness that follows. Every star that has ever shone, every planet that has ever formed, and every life that has ever existed will be forgotten in a universe that continues expanding into ever greater emptiness. Quantum mechanics suggests that even during heat death, rare fluctuations could theoretically recreate complex structures, including entire civilizations, with false memories of rich histories. However, these fluctuations would be separated by time intervals so enormous that they would occur less frequently than once per 10 to the 10 to the 50 power years, making them effectively impossible on any meaningful timescale. The heat death plateau represents the ultimate triumph of entropy over order, a cosmic state where the universe has exhausted all possibilities for creating complexity or meaning. It is not destruction in any dramatic sense, but rather an eternal, unchanging emptiness where nothing significant can ever happen again. Vacuum decay bubbles. Vacuum decay bubbles represent expanding regions of altered physics that could be propagating through the universe right now, invisible and undetectable until they arrive. These bubbles form when the Higgs field transitions from its current metastable state to a lower energy configuration, creating spherical regions where the fundamental laws of nature operate differently than in our observable universe. The bubble formation process begins with quantum tunneling, a phenomenon where particles can spontaneously transition through energy barriers that should be impossible to cross according to classical physics. If the Higgs field tunnels to a lower energy state at any point in space, it creates a small bubble of true vacuum surrounded by our false vacuum. This bubble then expands outward at the speed of light, converting everything in its path to the new physics. The bubble wall itself would be a thin boundary layer where the transition between old and new physics occurs. This boundary would be incredibly energetic, containing enough concentrated energy to potentially outshine entire galaxies as it passes. However, the energy would be released in forms that might not be detectable by instruments designed to observe our current physics. Inside a vacuum decay bubble, the properties of matter and energy would be fundamentally different. The masses of particles could change dramatically, making atoms unstable or preventing them from forming altogether. The strength of fundamental forces like electromagnetism and the strong nuclear force could be altered, causing all chemical bonds to break and atomic nuclei to disintegrate. What makes vacuum decay bubbles particularly terrifying is their complete unpredictability and inevitability. Multiple bubbles could be expanding through the universe simultaneously, each one invisible until it arrives. There would be no way to detect an approaching bubble, no method to shield against its effects, and no possibility of escape once the transition begins. The expansion rate ensures that once a bubble forms anywhere in the universe, it will eventually encompass all of space. Even if a bubble formed in the most distant observable galaxy, it would still reach Earth eventually, though the journey might take billions of years. The universe could already contain numerous expanding bubbles of altered physics, racing toward us at light speed through the cosmic void. Each bubble represents a complete rewriting of reality, transforming regions of space into domains governed by alien physical laws that could make the existence of matter, energy, and structure as we know them impossible. Cosmic strings. Cosmic strings are hypothetical one-dimensional defects in spacetime that could stretch across the entire observable universe, possessing gravitational effects so extreme they could slice through planets and stars like invisible cosmic razors. These theoretical structures would have formed during phase transitions in the early universe, when the fundamental forces separated from their unified state in the first fraction of a second after the Big Bang. A cosmic string would be incredibly thin, with a width smaller than a proton, but potentially millions of light-years in length. Despite their microscopic thickness, cosmic strings would contain enormous amounts of mass energy concentrated into their linear structure. A single meter of cosmic string could have a mass equivalent to Mount Everest, creating gravitational effects that warp spacetime along their entire length. The gravitational field around a cosmic string differs fundamentally from that of normal matter. Instead of creating a spherical gravitational well like a planet or star, a cosmic string would create a conical deficit in spacetime. This means that space around the string would be missing a wedge-shaped section, causing light rays and matter to be deflected as they pass nearby, but without the typical attractive force of conventional gravity. If cosmic strings exist, they would be moving through space at significant fractions of the speed of light, oscillating and vibrating as they travel. These oscillations would generate gravitational waves, ripples in spacetime that could potentially be detected by sensitive instruments. However, the strings themselves would be essentially invisible, detectable only through their gravitational effects on surrounding matter and light. The most terrifying aspect of cosmic strings lies in their potential for destruction through direct collision. If a cosmic string passed through a planet, star, or any other object, it would slice cleanly through without slowing down or being deflected. The gravitational shear forces would be so intense that they would tear apart atomic bonds and nuclear structure, leaving behind a perfectly smooth cut through whatever material the string encountered. A cosmic string collision with Earth would be instantaneous and absolute. The string would pass through the planet in a fraction of a second, potentially splitting it into two separate pieces that would then drift apart. There would be no warning, no way to detect the approaching string, and no possible defense against its effects. The cut would be so clean that initially, the two halves might not even realize they had been separated until gravitational forces began pulling them apart. The Boötes Void. The Boötes Void is one of the most profoundly empty and eerie structures ever found in the universe. Discovered in 1981 by a team of astronomers led by Robert Kirshner during a redshift survey of galaxies. Located roughly 700 million light-years from Earth in the direction of the Boötes constellation, it stunned researchers with its sheer absence of galaxies. The void stretches approximately 330 million light-years in diameter. To contextualize this scale, the Milky Way galaxy is about 100,000 light-years in diameter. That means you could place more than 2,000 Milky Ways side by side across the Boötes Void. Its volume is estimated at over 236 billion cubic light-years. If the United States were projected into this space, it would fit more than 2 billion times over, making it one of the largest known structures of emptiness in the observable universe. What makes the Boötes Void so profoundly unsettling is not just its size, but the level of emptiness it contains. In a region of that volume, scientists would typically expect to find around 2,000 galaxies based on standard cosmic density. Instead, fewer than 60 galaxies have been detected. That's less than 3% of what should be there. It's not just underpopulated, it's a cosmic desert on an incomprehensible scale. One of the prevailing theories suggests that the void was created by the gravitational merging of several smaller voids early in the formation of the universe. This would have left behind a massive bubble of near-total nothingness. However, this theory doesn't fully explain the scale of the void, nor why it's so geometrically smooth. The Boötes Void is terrifying, not because it's dangerous, but because it challenges everything we think we know about the structure of the cosmos. It suggests that the universe might contain regions completely cut off from galactic activity places, where, if you were placed inside, there would be no visible light in any direction, no stars, no galaxies, no cosmic radiation strong enough to illuminate the dark. From a human perspective, it's one of the most extreme expressions of cosmic isolation ever discovered, a reminder that the universe is not uniformly vibrant, but stitched together with patches of pure, silent, endless void. The Eridanus supervoid. The Eridanus supervoid is one of the most bizarre and colossal voids ever identified. First identified in 2004 by astronomers studying data from the Wilkinson Microwave Anisotropy Probe, which maps the cosmic microwave background, the faint afterglow of the Big Bang. In the direction of the Eridanus constellation, they noticed a large cold spot, significantly cooler than surrounding regions of the sky. Further investigation revealed that this wasn't just a temperature anomaly, it coincided with a massive underdense region in space. Located approximately 1.3 billion light-years away, the Eridanus supervoid is believed to span nearly 1 billion light-years across, making it one of the largest voids ever discovered. For scale, a beam of light would take 1 billion years to travel from one end to the other, which is more than 7 times the current age of multicellular life on Earth. And, if a single banana were 20 centimeters long, it would take 5 quintillion bananas to stretch across the Eridanus supervoid. Unlike typical voids, which are already sparse, this supervoid stands out for its extreme size and the depth of its emptiness. It contains significantly fewer galaxies than expected for a region of that magnitude. What makes it so disturbing is the potential connection between this void and the cold spot in the CMB. Some scientists theorize that light traveling through the underdense region loses energy, creating the cold spot via the integrated Sachs-Wolf effect. However, this explanation is not universally accepted. The phenomenon remains scientifically controversial, leaving room for alternative interpretations, including ones that extend beyond the boundaries of known physics. Some speculative theories suggest the Eridanus supervoid could be evidence of a collision with another universe, or the result of unknown large-scale forces at work. Even in more conservative models, its vast emptiness forces cosmologists to confront the possibility that our understanding of how matter distributed itself after the Big Bang might be incomplete. The Eridanus supervoid is terrifying, not because of what we know about it, but because of what we don't. It's a billion light-year-wide question mark stitched into the fabric of the universe, defying conventional structure and hinting at forces that may exist far outside our current comprehension. The Great Attractor. The Great Attractor is a gravitational anomaly so powerful that it's redirecting the paths of entire galactic superclusters, including our own. First detected in the late 70s and early 80s, not by direct observation, but through its gravitational influence on galaxies. Astronomers noticed that the Milky Way and hundreds of thousands of other galaxies were all moving toward a specific region of space at a speed of approximately 600 kilometers per second, fast enough to travel from Earth to the Moon in 11 minutes. This mysterious pull couldn't be explained by any known mass within the visible universe at the time. The problem was that the source of this immense gravitational force lies behind the zone of avoidance, a region obscured by the dense gas, dust, and stars of our own Milky Way galaxy. This made it incredibly difficult to observe directly using optical telescopes. The region itself is located about 150 to 250 million light-years away. To put this in scale, the light currently reaching us from the Great Attractor started its journey around the time early dinosaurs appeared on Earth, near the constellation Norma, at the center of the Laniakea supercluster, which includes our Milky Way. What makes the Great Attractor so terrifying is that we are influenced by a force we cannot see. It's a gravitational anomaly, possibly a supermassive concentration of galaxies and dark matter, dragging entire galaxy clusters, including ours, toward it. Later studies identified the Norma cluster as a key contributor, but the full structure and scope of the Great Attractor remain hidden. Adding to the unsettling mystery, some scientists believe that the Great Attractor is itself being pulled toward an even larger and more massive structure, the Shapley supercluster, which lies farther away in the same general direction. This recursive pattern structures pulling on structures reveals a cosmic tug-of-war that we don't fully understand. The horror of the Great Attractor lies in its invisibility and scale. It's not a place we can travel to or observe directly with ease, yet it exerts force across hundreds of millions of light-years, dragging entire galactic systems like leaves in a current. From a human perspective, it represents the existential terror of being caught in the flow of a universe guided by unseen forces that may never be completely revealed. Gamma-ray bursts. Gamma-ray bursts are among the most violent and destructive events ever observed in the universe. First detected in the late 1960s by military satellites monitoring nuclear tests, these sudden, high-energy flashes of gamma radiation have since become a central focus of astrophysical research. They occur unpredictably, last anywhere from milliseconds to several minutes, and release more energy in a few seconds than our Sun will emit in its entire 10 billion-year lifetime. That's the equivalent of 100 billion trillion nuclear bombs detonating at once. Long-duration GRBs can release as much energy as the entire Milky Way galaxy produces in a year, all focused into a narrow beam. What makes GRBs so terrifying is not just their sheer power, but their reach. A long-duration GRB, typically caused by the collapse of a massive star into a black hole, can send a collimated jet of radiation across vast stretches of space. If Earth were ever caught within such a beam from a nearby source, the results would be catastrophic. The gamma radiation would strip away the ozone layer, flood the planet with lethal UV rays, and likely trigger a mass extinction event. Some researchers even speculate that a GRB may have contributed to past extinction events in Earth's history. GRBs are divided into two primary types: long-duration bursts linked to hypernovae, and short-duration bursts thought to result from neutron-star collisions. Both scenarios are catastrophic, but it's the unpredictability and intensity of the beams they emit that elevate them to one of the most frightening cosmic threats. We can't see GRBs coming. They arrive without warning and are often observed only after the damage would already be done. There's no known way to shield a planet from their effects, and they can originate from galaxies billions of light-years away, making them one of the few threats capable of causing devastation from unimaginable distances. The event horizon. The event horizon is not a place in the traditional sense, but a boundary in space-time surrounding every black hole. It was first described mathematically by Carl Schwarzschild in 1916, following Albert Einstein's publication of general relativity. This invisible perimeter marks the point at which gravity becomes so intense that nothing, not even light, can escape. Once crossed, return is impossible. The event horizon is not a surface or a wall. It has no physical structure. It is a mathematical threshold, a point of no return. Anything that passes this boundary is irrevocably pulled inward toward the black hole's center, toward the singularity. From the outside, an object falling into a black hole appears to slow down, freeze, and fade as it approaches the event horizon due to time dilation. From the object's own perspective, it crosses the boundary quickly and is stretched, compressed, and ultimately destroyed by tidal gravitational forces, a process known as spaghettification. The terror of the event horizon lies in its finality. It is the edge of causality. No signals can pass from inside to out, no observations can be made beyond it. In essence, it marks the limits of physical law as we know it. Space and time lose meaning beyond the event horizon, and our mathematical tools no longer function. We never actually observed an event horizon until 2019, when the Event Horizon Telescope released the first direct image of the shadow of a black hole in galaxy M87, located 53 million light-years away. What we saw was not the event horizon itself, but its shadow, a circular region surrounded by glowing gas being pulled into darkness. What makes the event horizon one of the scariest places in the universe is its role as a cosmic point of erasure. It is where the known ends and the unknowable begins. A frontier not just of space, but of reality, where even information, the bedrock of physics, may be destroyed. The singularity. At the heart of every black hole lies the singularity, a single point where mass is compressed into infinite density. While the concept of black holes was derived from Einstein's theory of general relativity in the early 20th century, the singularity itself was more rigorously defined in the 1960s through the work of Roger Penrose and Stephen Hawking. Unlike the event horizon, which can be observed indirectly, the singularity remains completely hidden and inaccessible to observation. The singularity is where all known laws of physics break down. General relativity, which governs the behavior of gravity on large scales, predicts infinite curvature of spacetime at this point. At the same time, quantum mechanics, which governs the behavior of particles at the smallest scales, has no way to describe or handle this infinite density. There is no unifying theory that can explain what happens here. This is known as the problem of quantum gravity. Inside the event horizon, every path in space leads inevitably toward the singularity. No matter what direction you move, space-time itself funnels you toward the center. As an object approaches, it is subjected to intense gravitational gradients. These tidal forces become so extreme that they stretch and compress matter until it is destroyed. From a scientific standpoint, the singularity is not just a place, it is the breakpoint of reality. Concepts such as time, space, causality, and physical existence become meaningless. This isn't just a theoretical flaw in our models. It is a real, physical destination that may exist in the cores of countless black holes throughout the universe. What makes the singularity so terrifying is that it embodies the limits of human knowledge. It is the point where mathematics ceases to function, where observations cannot be made, and where even the fabric of space-time collapses into something we don't understand. For humanity, the singularity is not only a destructive gravitational abyss, it is the ultimate unknown. Sagittarius A star. Sagittarius A star is a supermassive black hole located at the very center of the Milky Way galaxy, approximately 26,000 light-years from Earth in the direction of the Sagittarius constellation. Its existence was first suspected in the 1970s due to strong radio emissions detected in that region. In 1974, Astronomers Bruce Ballack and Robert Brown officially identified Sagittarius A as a compact radio source using the National Radio Astronomy Observatory. The black hole is estimated to have a mass of about 4 million times that of the Sun. Yet, it is confined to a region no larger than our solar system. Its gravitational influence is so powerful that it affects the orbits of nearby stars, particularly a group of fast-moving stars known as S-stars, which orbit the black hole at incredibly high speeds. This motion provided some of the clearest indirect evidence of its existence long before direct imaging was possible. In 2022, the Event Horizon Telescope released the first ever image of Sagittarius A's shadow, confirming visually what decades of radio and infrared data had strongly indicated: that a supermassive black hole lies at the heart of our galaxy. What makes Sagittarius A so uniquely frightening is its proximity. While many of the universe's most dangerous objects are billions of light-years away, Sagittarius A resides at the core of our own galactic home. Its event horizon marks the boundary beyond which anything, including light, matter, and even information, is lost forever. Anything that crosses this boundary spirals toward the singularity at its center. Though Earth is currently far enough away to remain unaffected, Sagittarius A serves as a constant reminder of the quiet but destructive forces operating within our own galaxy. It is capable of devouring stars, warping time, and altering the structure of surrounding space. Should it ever become more active, say, by absorbing a dense cloud of matter, it could release powerful bursts of radiation with galactic consequences. Sagittarius A represents a cosmic predator hiding in plain sight. It is dormant, invisible in regular light, and largely silent, yet it exerts gravitational control over everything in our galaxy. Its presence is a chilling demonstration that even the heart of the galaxy is ruled by forces we can barely comprehend. The Big Rip. The Big Rip is one of the most haunting theoretical endings to the universe, an ultimate doomsday scenario driven not by fire, cold, or collapse, but by the relentless acceleration of cosmic expansion. First proposed in the early 2000s, the theory stems from the observation that the universe isn't just expanding, it's expanding faster over time, propelled by a mysterious force known as dark energy. What makes the Big Rip so terrifying is the implication that this acceleration might not level off or slow down. It could continue increasing indefinitely. If dark energy's influence grows stronger over time, then its repulsive force could eventually overcome every form of gravitational, electromagnetic, and even nuclear binding. Structures we consider permanent galaxies, stars, planets, atoms, would be systematically torn apart. It starts slowly. Galaxies drift further from one another. Then, galaxy clusters disband. In the final moments, solar systems are pulled apart, planets ripped from their orbits, and stars torn into fragments. Closer to the end, even atoms are no longer safe. Molecular bonds break, protons and neutrons dissolve. The fabric of matter itself disintegrates. In the last instance, before the final rip, space-time stretches infinitely fast. The laws of physics break down not at a single point, but everywhere, all at once. The Big Rip isn't just an ending, it's an unraveling. A scenario where the universe doesn't collapse into a singularity or fade into heat death, but tears itself to shreds from within. And the most chilling part? We don't know yet if it's coming. The strength and behavior of dark energy remain one of the biggest unknowns in cosmology. If it continues to accelerate unchecked, the Big Rip could be billions of years away, or, in a far more unstable model, it could occur sooner than we expect. The Big Rip represents a uniquely unsettling fate. Not a bang, not a freeze, but a cosmic shredding, where everything we know is ultimately unmade by the very thing that keeps the universe growing.